Today we are very happy to have Brian Swingle, who will be telling us about magic and wormholes. We plan to go to dinner. If you are interested in going to dinner, please send me an email by 4:30.
Thank you. Good to see you all. Thanks for having me. Yeah, today I'm going to tell you about a relationship between what's called quantum magic, which I'll explain what that is in a little bit, and wormholes in simple models of quantum gravity. This is based on two papers in the last few months, one with my student Valerie, which I'll mostly focus on today, and then one also with my collaborators Alejandro and Martin. And yeah, you'll see the relevance of this chemical picture a little bit later on. Get started. So yeah, here's my collaborators. As I said, Valerie's my student. She's graduating this year, and sorry, it should be Alejandro, not Javier. Sorry, this is a different paper. And yeah, I've put more details in the slides than I can go through. So if you want to, look at the slides, they're on that website there. And yeah, let's get started. So let's just set the stage. So I'm going to be thinking about a quantum many-body system today. It's a system of a bunch of fermions and fermions. And for this many-body system, there's a very natural set of operators, which I'll call Majorana strings. They're just composed of strings of these operators. So for each Majorana fermion from 1 to n, you may choose whether it's present or absent in your string. That's indicated by these little coefficients here, a1 through an. And so this set of strings is one-to-one correspondence with a set of binary vectors, n-dimensional binary vectors. So this is a complete basis of Hermitian operators. And in this talk, we're going to think about the thermal one-point functions, that is the expectation value of these operators, and a thermal state. Okay, so that's the basic ingredients of the talk. And what we're going to think about specifically is ensembles of Hamiltonians and the statistical properties of these thermal one-point functions over this ensemble of Hamiltonians. Okay. And I'm going to explain to you what this has to do with this idea of magic, and then separately what it has to do with wormholes, and we'll see how they come together in a minute. Uh-oh. Computer. Hold on one second.
Is it connected to the Zoom?
It kicked me off the internet, so. Join. Previously, I was getting free Wi-Fi from IIS, and now it's making me agree to some.
Did I get it wrong?
Let's see if this works.
I have it wrong. So
This. And there we go. Okay. It's we're good. Yeah. So we're going to consider the properties of these strings. Now, okay, that's the just wanted to lay out the objects, but let me explain why we care about these things first of all. So one reason to care is that they fully specify the many-body quantum state. So if you know all of these expectation values, then you know the entire quantum state. Now, in a many-body system, there's exponentially many of these, so it's a lot of data to keep track of. And experiments don't normally access all this information. They're normally looking at few body measurements. So it's sort of there, but hard to see, hard to keep track of. One place where we've thought a lot about this, the community in the past, is in the context of what's called information scrambling. So you imagine you have some operator, V, let's say, which is initially a simple operator composed of a few major fermions, and you're going to evolve it in time. And what you find is that it spreads out and it has a superposition of all kinds of different fermion string operators. And tracking the dynamics of these expansion coefficients is a productive way to keep track of how that operator is getting larger and more complicated as a function of time. So separately, you also can, in experiments, measure very many-body observables of this type. For example, here's a picture of a bunch of cold atoms in a trap in Mark Schreiner's lab. And this is a measurement, a complete measurement of the state of the system in the Z basis. So you've literally imaged every single site in some lattice and said, is there an atom there or not? So, of course, this is sort of just one of these strings effectively. But nevertheless, we can access this data in experiment. And so that's another reason to think about it. But today I want to focus on two different topics, which is how this data shows up in the context of what I'll call quantum magic. And again, I'll explain what that is in a second. And then how it also shows up in closed universes and wormholes and how these are related. That's kind of where we're going. Just to give you something concrete, we're going to think about this in the context of the Sachdev-Ye-Kitaev model. I think the discussion I'll give on the magic side is more general, and you could apply it to other kinds of models. But this model is particularly nice for its tractability and because it has this gravitational connection. And the way to think about this model, in the case that I'm showing here, we have what's called Q equals 4-body interactions. You have a bunch of fermions, and you have all possible 4 fermion interactions with some Gaussian random coefficients. We can have a 2-body version of this or a 6-body version or anything, but here's the 4-body version. And so I'm going to study these thermal expectation values for thermal states of this Hamiltonian. And it's the J's, these random couplings, that define my ensemble of Hamiltonians and then indirectly define an ensemble of thermal one-point functions. So here's the plan. I'm going to first review for you this idea of magic, which I think is probably a concept that's not familiar to most people in high energy physics. I'm going to review that idea and discuss kind of some of the recent developments. Then I will explain how to calculate this quantity or some measure of this quantity in the SYK model. That'll be the first paper that I flashed above with my student Val. And the key technical result there is that these thermal one-point functions are going to behave like real Gaussian random variables. So once we know that, and once we calculate their variance, then we sort of know everything about the magic in the system. And then separately, I'm going to discuss how when you make the temperature low, you can reproduce these SYK calculations with a gravity calculation involving wormholes and matter propagating on wormholes. Okay, and then if there's time at the end, I'll discuss a little bit what this has to do with the recent stories about closed universes. We'll see how far we get. Okay, and if there's any questions, especially of the magic stuff, please stop me. I'm happy to dive into that. I think it's probably an unfamiliar topic, so All right, so let me start out by trying to connect to something that you're probably a little bit more familiar with, the idea of entanglement. So entanglement as a resource. So this idea of resources in terms of a way to view physical theories in terms of some quantity that you'd like to keep track of or measure. And in these resource theories, there are a concept of free resources or free states. In the case of quantum entanglement, it would be unentangled states. So you're always allowed to add unentangled states to your system from this resource perspective of entanglement at no charge. And then you want to have measures, for example, like the entanglement entropy, which tells you how much of the valuable resource entanglement you have in your system, right? And you'll notice that crucially, if I add free states to an entangled system, that doesn't change the entanglement. Okay, so that's part of the axioms of the game in this context. And so we think of entanglement as like a fuel, something we're going to burn or use up to do some interesting task. For example, if you want to do quantum teleportation, that requires 1 unit of entanglement. If you want to win a multiplayer quantum game, which is another version of the Bell inequality, if you like, that requires entanglement. If you want to do a general quantum computation, that requires entanglement. Okay. And we know in the context of holography that it's also related to geometry of spacetime. So in all, yes?
Question, in all your examples in your second paragraph, one needs many copies of the system to use entanglement as a resource.
No, not necessarily.
Is there a single copy way of making use of?
Yeah, I mean, teleportation and these multiplayer games often, involve 1 or a few copies. You need a specific kind of entanglement. So if you had some more general kind, I might need to do a process of distillation or preparation. If given sort of idealized units of entanglement, you can do something with just 1 or a few copies. Okay. So the second bullet point is kind of, we want to use entanglement as a fuel for doing something interesting physically. But conversely, from the point of view of simulating a system using classical numerical techniques, low entanglement is sort of an opportunity. It says if we can have an approach to the simulation problem which leverages that low entanglement in some way, then we can make some progress on simulation. So an example of this are tensor networks. They use the fact that certain states of interest in nature are naturally low entanglement. And then we can use this low entanglement ansatz to say something about the physical system. Okay, so from this point of view, magic is the resource theory of something called non-stabilizerness. Okay, that probably makes no sense to you, so let me try to explain what this is. So let's go back to our fermionic system. I need to define 2 notions for you. One is what are called fermionic Clifford circuits, fermionic stabilizer states. And so let me start with Clifford's. This is, I think, the easiest place to think about this. So we have our Majorana strings here. UA, remember A was just telling me which fermions were present or absent in the string. And the Clifford group is a subgroup of the full unitary group that maps a string to another string. Okay, so for each string you can put in there, you must get 1 other string out. Right? A general unitary transformation will turn a string into a superposition of all possible strings. But the Clifford group is special. It takes 1 string and maps to another string. And so if you think about keeping track of where the strings are getting mapped, you have a much smaller problem to keep track of now for this Clifford group. You only need to follow where these n-component vectors are getting mapped under the Clifford operation. So this is still doing some transformation on the full many-body Hilbert space, but it's much more efficient to track what this transformation is doing in the Heisenberg picture by simply following where these operators get mapped to. So essentially, you can keep track of this transformation with an n by n matrix that maps the input A to the output A, the input label of the string to the output label. And interestingly, these transformations can still make lots of entanglement, but they're nevertheless efficiently trackable classically. So that's kind of a preferred set of unitaries. Now we can define a preferred set of states, the stabilizer states, by starting with some fixed special state, say a state where the fermions are equal in pairs to 1. This is the analog of like the all zero state or the all up state for a bunch of spins. Then we take this initial state and we act with any Clifford unitary on it. That produces the set of pure stabilizer states. Yes.
So U is supposed to be a unitary, which is just given by a particular string.
Sorry, the unitary you could think of as being defined by a matrix, which tells you how to map the input string index to the output string index. It's an n by n matrix.
I mean 2 to the n, right?
No, that's the crucial thing, right? Because this fermion string is specified by an n component vector. If I have equation 1 there, then I have an input vector of size n, and I have an output vector a prime, also of size n. And the mapping you can show is linear. So there's just a matrix here which defines that mapping. And so now you can keep track of the dynamics with an n by n matrix instead of a 2n by 2n matrix.
Sorry, U is any unitary that maps operators defined by strings to other such.
Yes.
So for example, it could include a permutation of your.
For example, yes. Other questions?
Does it map even elements to even?
We don't impose that restriction here, but in the third point, yeah, we can consider the subgroup which preserves fermion parity. And in that case, you can show, actually we showed in this recent paper from a year or two ago, that the group, the Clifford group in that case, can be mapped to the orthogonal group over Z2. Okay, so it's just these matrices M are by, every entry is 0, 1, and they're orthogonal. Okay, so they just satisfy the orthogonality condition, but over Z2.
And these stabilizer states can have entanglement between the different.
Yeah, so bell pairs are stabilizer states, for example, and you can have maximal entanglement between, say, n qubits with n other qubits, or 2n fermions with 2n fermions. So you can have lots of entanglement, but nevertheless, this is not the most generic possible unitary. These are not universal for quantum computation. They're not able to produce any unitary you like. It's just a very special subclass of all the unitaries, or a very special subclass of all the states. But nevertheless, it's a very interesting subclass. For example, why do people care about these things? Many quantum error correcting codes can be understood in this language. They also provide a nice toy model for dynamics. So people study random circuits or other kinds of interesting dynamical problems, where rather than considering most general possible circuit, you consider random Clifford circuit, for example. And then you can efficiently simulate the dynamics classically and learn something about your quantum system. And of course, some of the things you learn might be special to the Clifford setting, but other things like entanglement growth might be more generic. And so maybe you could learn something about entanglement growth in a very large quantum system from this special situation. Other questions? Maybe, it's useful to think, if I combine entanglement and magic together, right, magic tells me how far away I am from this situation. And entanglement tells me how far away I am from product states. If the entanglement is too low down here, then I have tensor networks, let's say, that can simulate the system. If the magic is too low, then I can do some sort of Clifford simulation of the system. So somewhere up here is kind of the hard region, where you have both magic and entanglement. That's the region where plausibly something difficult is going to happen, which we can't easily access using classical simulation tools. Whereas if it's, again, low entanglement, maybe we can use tensor networks. If it's low magic, maybe we can use Clifford states to approximate the dynamics. So let me just give you an example. So here is, this is a single qubit now. So there's a standard kind of story for a single qubit. Everything works the same way. The gray region here is the Bloch sphere. This polyhedron is what's called the stabilizer polytope. And it's defined as follows. These dots are stabilizer states, the pure states, the eigenstates of Z, eigenstates of X, eigenstates of Y. And then the polytope is the mixtures, the mixed states that are obtained by mixing these different pure states together. So it's inscribed inside the Bloch sphere, but the only place it touches the Bloch sphere are these special pure stabilizer states. If you say have some mixture, some superposition of 0 and plus, you'll be in some other direction of the Bloch sphere and you won't be a stabilizer state. And so the idea of like, how do I quantitatively measure magic is I want to something like measure the distance between my state and this polytope. If I can have some quantification of that, that would be something like a measure of magic. So here's one such measure.
Sorry, was it the inside of that polytope or on the surface of the polytope?
It's inside. Yeah, everything inside is a mixture of stabilizer states. And so, in other words, if you have a quantum state inside there, you can model it as classical randomness, that is the mixture, plus stabilizer states. Okay, so that's sort of viewed as easy. Quantumly easy. Okay, so as I said, the general idea of measuring magic is to find some quantity that essentially diagnoses how far away you are from this polytope, from the stabilizer polytope. The trouble in this business is that many of them are very, very hard to calculate. They involve optimizations over some very high dimensional space, or other difficult to calculate quantities. But one that we can actually access with our physics tools is called the robustness of magic. And it's defined the following way. So you have a state, rho here. And the idea is you want to decompose rho in all possible ways as a mixture of states in this stabilizer polytope. Okay, so just write it in some way. The trick is that these coefficients C need to be negative in general. If they're all positive, then it's just a mixture of stabilizer states and you're in the polytope. So the only way this can describe every possible state is if you allow some of them to be negative. So the same is true actually of entanglements. You may know that if you want to describe a most general entangled state, you can do so with mixtures of product states, but you need to allow negative coefficients. So it's not really a mixture anymore. Yes.
So this definition of magic refers to a particular choice of stabilizer states, or yeah, to
That's right.
computational basis.
That's right. Yeah, it is. There is a serious degree of sort of basis dependence, and this is something that can make sense in a given computational model for a quantum computer. But from the point of view of a physical system, we need to think a little bit about whether this restriction makes sense.
What could refer to a choice of for a particular Hamiltonian than the stabilizer.
Yes. Yeah.
Markov the measure of magic is reflected entropy minus usual information, or is it not a measure? But
I don't know. My instinct is probably not, but I'm not sure. It's a good question. Okay, but so here we make the decomposition, and then we compute the one norm of the coefficients. Okay, so we just take the absolute value and add them up. And so if it's a stabilizer state, then these coefficients can all be positive. When you add them up, it's normalized, you just get 1. So this robustness is 1 for any stabilizer state. But if some of the C's need to be negative, then this robustness will be larger than 1. Okay. So that will be the thing we're going to look for. We're going to look for a situation where this robustness is larger than 1, and that will signal that there is definitely magic in the system. Yes.
The term magic seems unintuitive because it's generic to have magic. By this definition, virtually any state is magical.
Yes, you're right. You're right. Yeah, the history of this is interesting. And yeah, well, I'm not an expert in the history, but, or, I don't want to speak for the founders of this subject, but these Clifford operations, despite seeming very special, are very natural for some kinds of systems. And they can be done, for example, in a way that is fault tolerant. So it's easy to do them even in the presence of errors in a way that doesn't propagate the errors. So for historical reasons, people were very interested in this particular set of gates. It includes things like a controlled knot, like the Hadamard gate, certain classic gates, and many interesting quantum algorithms can be built mostly from these gates. And then there was a paper of Brandeis and Kitaev where they sort of said that if you have these extra magic states, you inject them into the computation, now you can do something universal. So they were sort of seen as this magic ingredient or magic fuel that, enables universality. But of course, I agree with you that from the point of view of pick a random state, pick a generic state, it's very highly magic. Okay. So I just said this. So yeah, this idea goes back a long ways. As far as I know, in sort of 2020, this was first studied in the many-body context. So some collaborators and I looked at it in the 3-state Potts model. And there, briefly, the idea was you have something like Hamiltonian, which is minus G X minus Z dagger Z, where X and Z are clock and shift operators for Z3. And the idea is as you dial G, well, if G is very large, it prefers the X basis, which is a stabilizer basis. If G is very small, it prefers the Z basis, which is also a stabilizer state. So you might expect that as you tune G, this system will go from being sort of stabilizer to stabilizer, but with something very non-stabilizer in the middle. And we showed that if you tune to the critical point, the magic is spiking in this system. Okay. And so we said, okay, somehow, in this case, the 3-state Potts CFT seems associated with magic in some interesting way. And then separately, around the same time, there was a discussion by Liu and Winter in which they sort of started building a framework for how to calculate many-body magic beyond what was known at the time, apply to some other interesting cases, for example, symmetry-protected phases. And since then, there's been some enormous explosion of interest in this. I think this is mostly driven by people wanting to understand what are the resource costs for simulating quantum many-body systems in this magic framework. And then separately, if something's low magic, can I, design like a simulation method that takes advantage of that? Something like tensor networks for magic. Yes.
Is there a particular reason why you skipped the icing CFT and went to the 3-state Potts model for investigating this?
Yeah, there is a particular reason, which is that 2 is an even prime. And that turns out to cause a lot of problems in the theory. So yeah, for most primes, there's a nice structure, but for even prime, it turns out that the theory of magic and stabilization is much more complicated for qubits than for qubits. For example, there's something called a discrete Wigner function, which you may be familiar with from the theory of Gaussianity, or the theory of oscillators. In the oscillator setting, if the Wigner function is positive, it's a Gaussian state. So in the qubit case, there's a discrete Wigner function, which if it's positive, it's a stabilizer state. And that's true for qubits or for 5-dimensional or 7-dimensional, any prime power, any prime, except for 2. And in that case, it's not true that this Wigner function is, the positivity implies, or the negativity implies it's not a stabilizer state. So there is something special there. And part of what these people did and what this like stabilizer ring entropy does is remove this barrier a little bit. So now you can look at qubits more naturally.
You still expect something qualitatively similar.
Yeah, so we still absolutely expect the same physics, but we just didn't have a clean way of extracting it, of measuring it. Okay, so let me explain now how we calculate this in SYK. And it's going to come down, so the technical problem is we need to evaluate these sums over moments of these thermal 1-point functions. So I already showed you that the case where R is equal to 1 was what was lower bounding the robustness of magic. So if we can calculate this for R equals 1, then we can lower bound it and learn that the system is magical potentially. But you see the calculation is non-trivial because there's a dimension factor in the bottom here. So we need this F1 to be big enough in order to get a non-trivial bound.
Sorry, did you define zeta?
Yeah, that was the thermal 1-point function.
Oh,
Sorry, let me write it again here. It's divided by. So it's just the expectation value of the chosen operator in the thermal state.
What is F1?
Sorry?
What is F1?
It's defined here, so it's just the sum over all choices of operator, all of these different strings of the 1-point function
in the state row.
in the state row. So just for all, we have n fermions, so there's 2 to the n strings. For each of those 2 to the n strings, you measure the expectation value of that string. It will usually be very small number, so these are very small numbers in general. We take the absolute value, we add them all up, and that's what this F1 quantity is. And I didn't explain why, but it turns out that stabilizer states just can't have a very large F1. It's just not possible. It's less than or equal to the dimension. And so that's where this dimension factor comes from. Essentially, the reason is that for a pure stabilizer state, at most, square root of 2 to the n of these things are non-zero. And so that's your dimension factor there. And then if you mix them by convexity, you can't do better than that. Can't get worse. Okay.
Xi phi is a function of the temperature or not?
In principle, yes.
Which temperature?
We just specify temperature. That's part of the data of the state. We're going to look at these quantities as a function of temperature.
Alpha is a function of temperature?
Where? Which?
Alpha.
Alpha?
Alpha. The left hand side.
Yeah, it's a function of temperature. It's a function of the state, which is a function of temperature.
Is rho a final temperature state?
Yes.
Oh, so in general, Xi phi would be the expectation.
I mean, this is the general definition, but we're going to consider finite temperature states.
I think you're going to consider a subset of qubits in a finite temperature state. Is that the idea?
I mean, just consider
The density matrix.
the density matrix, the thermal density matrix. Yeah,
The full system.
of the full system.
But if rho is general and you define zeta of A by trace of A rho, would that still hold?
Yeah, everything here. So these are definitions, and the red thing is a bound, and that holds in complete generality.
So in that case, then zeta would be defined by the trace of A rho.
Correct.
A rho.
Yes, exactly. Yeah. In general. You choose a state, you choose an operator, you take the trace.
Can you say one more time? So R equals 1 is non-magical,
Yeah, that's any stabilizer state has R equals 1.
and R cannot be greater than 1, or it could.
No, it can. So, I mean, we'll see explicitly that it's going to be bigger than 1.
It could also be less than.
No, it can't be less than 1. It's If it's a stabilizer state, it's 1. If it's any other state, it's bigger than 1.
So what's the significance of this lower bound then?
So this bound will only be meaningful, only be useful if F1 is big enough.
Oh,
It's certainly possible for F1 to be small. So for example, if rho were the maximally mixed state, then F1 would be just 1. And this bound would be true, but vacuous because we have a better bound. So only if F1 is large enough is this interesting. Yes.
To develop a little bit of illusion, if I take rho to be an identity matrix, an infinite temperature state.
Yes.
What would be R in that case?
In that case, R is 1 because it's a stabilizer state. And F would be 1, and this bound would be useless, but true.
Maximal, I mean, infinite temperature state. Why is that a stabilizer state?
Well, go back to the block sphere case. You could think of 0 and 1. They're both stabilizer states, and it's just a mixture of them. It's equal weight mixture of 0 and 1. So if I go back here, the center of the block sphere is like the deepest point inside the polytope. It's the most stabilizer state of all stabilizer states because it's just featureless.
There is some critical temperature to which the magic disappears.
In this, like if for example, you were considering a qubit in a magnetic field, for example, yes, there would be some temperature sufficiently high in which you would enter the polytope and then remain there as the temperature is further.
Yeah, but for large systems.
Yeah, for large systems, it's a question. That's the question that we will try to address. Yeah, I think it's generally not known whether there's this is sometimes called the sudden death of entanglement or magic. As you raise the temperature, it's known that the entanglement of the system has a sudden death, so it just suddenly goes away beyond some temperature because you're entering the product state polytope. And in the case of magic, this may also occur. For SYK, it turns out not to, but it's sort of subtle, as I'll discuss in a little bit. Okay. So again, this C quantity is the 1-point function for operator labeled by A. We're going to think about thermal states. And what we want to calculate more generally is moments of this thing, summed over all operators. And we're going to do that using replicas. So we have thermal circle, that's the purple thing here. That's my density matrix, thermal density matrix. The orange dot stands for my heavy operator, or my operator. We're going to have a bunch of copies of this. And then what we're going to compute is not this directly, but its average over the ensemble of SYK Hamiltons. That's what we can calculate. Okay, so how does that work? I'll just flash these technical details quickly. So we have our thermal density matrix here. For a given instance, we have our choice of operator. We raise it to the rth power. You can convince yourself this is a real number, so you don't need the absolute values. You do a little bit of gymnastics, and what you conclude is that this operator here, mu, is labeled by a choice of which fermions are included. You can convert this into a sort of expectation value where you now have R copies of the system, and the chosen fermions have their boundary condition flipped from antiperiodic to periodic. So you choose some subset of the fermions that defines your operator. What happens is that you have a sort of a thermal trace now on a larger R copy system where all of the unchosen fermions remain antiperiodic around the thermal circle. The chosen fermions become periodic. Essentially, you can see that because you just get a copy of the fermion for each replica from each factor of mu. And so you just get -1 to the F for each particular fermion that's included.
What happens if you compute this directly for R equals 1?
Yeah, you can do that, but then you find that it's 0. because that's essentially telling you that these things are zero on average. And so indeed, you can convince yourself that any odd power R is going to be zero. At least if you don't have the absolute value, that's where it does matter. And so what we want to compute are the even powers. That will tell us, for example, the variance or the fourth moment and so on. Okay, so I'm just gonna, again, flash kind of what you're gonna do. You have a bunch of replicas, so you introduce your collective field variables G and sigma, but now they have a replica index, if you're not familiar with this. And what happens is that you have, if W is the number of fermions that are present in your string, for W of those fermions, you have now periodic boundary conditions. You have a Pfaffian contribution, but with a periodic time derivative. For the remaining, you have the anti-periodic time derivative still. So you have the same kind of usual collective field action, but you've modified the boundary conditions of some fraction of your fermion. So we're still going to do the path integral. We're still going to evaluate the path integral at large N with the saddle point, but we've twisted the boundary conditions of some fraction of our fermions. And of course, when we do the ensemble average, it doesn't actually matter which fermions we chose in our operator. So only thing that matters is how many fermions are there. Everything depends just on the weight. This is kind of the same thing, but I want to emphasize that this was a lot of work. The operator inserted breaks time translation symmetry. So you cannot use Fourier modes anymore. You have to discretize in space, at least as far as we could tell. So this was kind of a huge pain, especially when there's lots of replicas. So here's what those derivatives are for the anti-periodic and periodic cases. You have some general action. You're going to find the saddle points of this action with this time discretization. And then these moments will just be whatever is the dominant action for R replicas minus R times the dominant action for one replica. So that's just a thermal partition function. This is our formula here. And so we just need to go to work to solve these equations, to find a bunch of saddle points, and then figure out which one is the dominant one for a given replica number and weight.
I'm slightly confused. You explained that the insertion has the effect of flipping the boundary conditions for a subset of fermions.
Yes.
And that recipe does seem like it has time translation symmetry.
Yeah, I guess the problem is that only some of the fermions are flipped. So some of them are periodic, some of them are anti-periodic. And that combination does not have translation symmetry. If you just had anti-periodic or just periodic, I agree with you. But when you have this combination, it turns out not to be the case. Okay, there's nothing about this slide except to just tell you we did a lot of work. So
Just to continue for some, I guess the reason for that is that the operator that flips some fermions doesn't commute with Hamiltonian.
correct, yes. So we had some exhaustive, well, I don't know if it's exhaustive, but we exhausted ourselves classifying initial conditions, different replica structures. We actually looked over all of this space to try to find, as many saddles as we could. You did all that work, and at the end of the day, we can get some nice solutions out. So here's an example with two replicas. So the collective field has 4 blocks: the 1-1 replica correlation, the 2-2, and then the between replica correlation. All diagonals. Coloring is sine. This is an example with beta equals 5 and weight 0.5. And the result that we find from this technical analysis is that these one-point functions behave like real Gaussians. So how do you see that in detail is like you look not at the 2 replica case, but the 4 replica case, and you find that the saddle in which you have 2 copies of the 2 replica saddle is a dominant one. And then if you account for permutations, there's 3 ways of doing that. And that 3 is the Gaussian, the real Gaussian 3. You can also check that the one loop determinant doesn't introduce any extra factors in this case. So the 4th one really is to leading order and 3 times the second moment squared. And that tells you that it's a real Gaussian. So all this work, all the higher moments, it ends up just boiling down to r equals 2 at the end of the day. Okay, so here's just what does it look like? So I'm plotting log of the variance squared and normalizing it by n. So that means the variance is e to the minus some function times n. Okay. And you can see here's there's being plotted as a function of the weight. Here's beta equals 0.5, so a pretty high temperature. It more or less looks like it's linearly or sort of decreasing roughly linearly with the weight. In fact, it's not quite linear. The slope approaches infinity here, but it's sort of roughly linear. So basically, as you add operators, the variance gets smaller and smaller and smaller, and the exponent is proportional to how many operators you have, roughly speaking. Quite reasonable. As you cool beta equals 1, beta equals 5, beta equals 20, eventually you start to bend back up as you increase the weight beyond half. And indeed, if you make the weight 1, you're just inserting minus 1 to the f for the whole system. Right. So actually over here, when weight is 1, this is the variance of minus 1 to the f. Okay. So not surprisingly, minus 1 to the f is a random variable in this system, and its variance is something, but it's pretty small. So this is one way of seeing, for example, that if you projected SYK onto the even parity or odd parity sector, you'd have the same free energy to leading order. Beta equals 20 is as far as I'm going to show you because basically we're losing control of the numerics past that. We don't have enough time points to resolve larger beta. So that's kind of the best we can do with our current technology. Okay, here's how we see that it's Gaussian. On the right is a Gaussian case, Q equals 4. I'm showing the action for 2 copies of the 2 replica saddle. That's the 2R2 versus this 4 replica correlated like 4 boundary wormhole type thing. And you can see it just has less action. The action is more negative, so the 2 copy action dominates. But something special happens when you consider Q equals 2 actually. It turns out that these 2 things have exactly the same action. And that's not an accident. There's a reason which arises from enhanced symmetry. In the Q equals 2 case, you actually have not just permutations of the replicas, but an orthogonal group that acts on the replicas. And so in this case, you can actually conclude that these variables are not real Gaussians. I mean, they're real, but there's some other distribution. No one seems to know exactly what they are. We can compute their moments. We have not done that yet. It's something we're working on. So in the literature, people realize that this case is not Gaussian, but they did not cleanly specify what the distribution is. And I think we would be able to figure it out here. It just involves integrating over the moduli space of these saddles and being careful about things. So that's sort of interesting, actually. But if you have chaos, if you have Q bigger than 2, then you get this Gaussian. Okay, let me show you one check to make sure we're doing things right. One thing we can do is compare the purity of the state computed 2 different ways. So in one way, here's the purity, trace rho squared. In one way of computing this, we just need essentially the partition function at beta and twice beta. This is a time translation random calculation, so it's straightforward to obtain this to very high precision. Okay, so we can calculate directly what is trace rho squared. However, we can also compute this using an identity, which is that if you take this matrix element, so this expectation value, the thermal 1-point function, you square it and sum over all operators, well, that's just equal to trace rho squared. That's a operator identity. So we can calculate it directly with the partition function, or we can calculate it by taking our data and doing the sum over the A, which is a sum over weight. And the way you can do that, well, you have the variance, which I showed here, and then you have a combinatorial factor for how many different ways are there to make strings of a given weight. But you can do this sum, you do it by saddle point, and then that's what's shown in the dashed lines here. So the bold lines are the kind of more exact calculation, the more precise calculation. The dashed lines are the numerics. For q equals 2, you can see it's just perfectly agreeing. For q equals 4, it agrees pretty well, especially at small beta, but as you get to higher beta, it starts to separate a little bit. And then for higher q's, we're not really converged that well, actually. So there's still a pretty significant deviation between these two calculations. So we wouldn't really trust these results, beyond, say, beta equals 5 or beta equals 10. I think that's a technical problem, but it's just what we were able to achieve. So I'll focus on q equals 2 and q equals 4 and what I say for it. One cool thing is that this sum is dominated by some critical value of the weight. It's like the value which makes the action stationary, with including the combinatorial factor. And at that value of the weight, the solution becomes time translation invariant again, but on 2 copies. So it's actually reproducing the 2-copy solution kind of coming out of nowhere, seemingly. It's kind of a cool feature.
Can you do the large Q analytically? Because sometimes large Q is.
Yeah, I think we can, but we have not done it yet. I tried to ask Claude to do it for me, but it was too hard. But yeah, I believe it should be possible. Okay, we did a lot of work. What do we conclude? This is the robustness again. Really, it's the lower bound here. So F1 over D, what I'm plotting on the y-axis is the logarithm of that. Okay. This is as a function of beta. So high temperature, low temperature. This line is what we're discussing. So if this quantity F1 over D is bigger than this line, then it's guaranteed to be highly magical, right? So that means at very high temperature, everything's below that line, and we're not guaranteed to be magical. But below some temperature, which depends on Q, different for Q equals 2 and Q equals 4, you pass above this line, then you conclude that there must be an exponentially large amount of magic in the system. Of course, I want to caution this does not mean that this state is not magical here. It just means this particular bound is not telling us that. In fact, we have other reasons for believing it still is magical here, but we don't have a way of measuring it good. There's no measure I know of that actually can kind of quantify it in a successful way here. Yeah.
So my intuition would have been that the integral model or the q equals 2 doesn't have very complicated entanglement structure, but here it looks like the opposite. Like it looks like it has the most magic.
Yeah.
What's wrong with my? Or I thought these integral one would have simple entanglement.
Well, yeah. So I think there's 2 comments. So first is it does have sort of simple entanglement, but we're not looking at entanglement directly. We're looking at this magic. And so from that point of view, if low magic states were like single strings of polys, q equals 2 is like some mixed, some random superposition of lots of different polys, right? Very directly.
But with simple entanglement, like EPR pairs are simple and also not magical.
Yeah, but the point is it's not EPR pairs.
Okay.
That's the point. Now, one can do different things. So one can define, for example, sort of magic minus Gaussianity. So you could say, take a state, allow myself to do any Gaussian fermionic unitary to it, minimize over all such unitaries, and that's like my non-Gaussian magic. And for that, this would definitely be 0, this Gaussian state. That's something else that's like something you deal with to try to get rid of this basis dependence or to ameliorate it, to make it something more basis independent. And we just don't know how to calculate that for q equals 4. But the other factor here is that this is much less entropy than this because there's no Gaussian entropy for Q equals 2. So if you were to take like a random pure low energy state, I would expect this to be much higher. I don't know how it would compare exactly to the Q equals 2 case, but it might be higher actually. Yes.
Just to discretely choose or fine tune your basis rather than averaging, you still lower this blue thing, but using a more clever.
Yeah, I think if you just did a Gaussian unitary at first to diagonalize to go to the energy basis,
Yeah, sure.
then
Sure.
you know,
But still,
maybe that's too fine tuned for you. I don't know. How much fine tuning do you want to do?
okay, I was just thinking.
But you know, we sort of, I don't think there is such a choice for Q equals 4. It would be nice to make that more sharp. And for the higher Qs, you know, these error bars are coming from our estimates of error from the purity plot. Since it's essentially the same action that's appearing, we just take that error as a sense of how far apart the action is from the true value. So for Q equals 2 and 4, we're pretty confident that it's above this threshold. But for 6 and 8, it's less clear. You could also do a simple theory of this. This is another, can be viewed as another response to the question. If it so happens that the weights which dominate this calculation have weight near 0.5, so they involve about half the fermions, then you can do a little theory and calculate that this quantity should be log 2/4 minus the second range entropy per particle. So this just follows because they're both controlled by the same weight, basically. You do this little calculation, and that's what the dashed line is here. That's the little theory. The solid is the numerics. And you see that they agree essentially perfectly for Q equals 2, and you know they're pretty close for Q equals 4. And so if you have a formula like this, you'll see that you always have magic no matter what S2 is, as long as it's less than the maximum value. So we suspect this is what happens for all of them at sufficiently low beta, but we just couldn't reach that point. Okay, let me quickly go through now the connection to wormhole. So the conclusion is SYK is very magical at low temperature, SYK4 at least. What does this have to do with wormholes? Well, the idea is we're going to interpret this two replica object between one copy and another copy of the thermal expectation value as being computed by some Euclidean wormhole with two boundaries here and here, which connects up in the interior. That connectivity is going to be a proxy of the variance, the non-trivial variance in the SYK. And I'm not going to talk about this, but the connection to closed universes is that if you continue analytically this wormhole from its midpoint, you get a closed universe, Big Bang, Big Crunch cosmology. Okay, so if we can quantitatively match these SYK objects to some gravity object, then we've gotten a wormhole calculation to match a gravity calculation, and we have a foothold then understanding what this cosmological object is from the SYK function. Let me just flash what the calculation is. So we're going to just model SYK. This is not meant to be an exact dual of the bulk of the SYK. We're going to model it as JT, gravity, coupled to one heavy particle, which is our operator, our mu, and then n light fields. So this is the model. And we're going to compute the 2-point function of the light fields as a proxy for the collective field in SYK by just summing over these light fermionic fields. But some of them are going to have antiperiodic boundary conditions, some of them are going to have periodic boundary conditions. Okay. So this solution for this, the solution I'm going to write down now does ignoring the light fields, but the JT coupled to the heavy particle, that has this well-known double trumpet solution. Okay, so here's the metric, dilaton. It's first written down by Stanford, thinking about sort of related topics, although not using the words magic. And here's my artist cartoon of what the solution looks like. So you have a thermal circle on the left, And on the right, you have a heavy particle, which connects the two sides with a geodesic. And then you have this wormhole geometry. And the throat is stabilized by this heavy particle to have this length. Okay, and so we're just going to calculate this correlations between a fermion field on the left at time tau and on the right at time tau prime by summing over all the geodesics that connect them. I just put some geometrical data here. Here are the formulas. And here I'm taking delta. I'm just going to take delta to be 1/4. I'm going to use the SYK value for the dimension. So I just fixed that.
Is the sum over geodesics correct for small dimensions, like you're saying?
I think it's essentially a fudge. In principle, you should put the mass there. That's the geodesic approximation at large mass. But if you put instead the dimension, then it seems to give the right answer or a better approximation to the right answer.
Sometimes it corresponds to summing over images.
Yeah, so you see, I mean, we have explicitly winding geodesics here, which include wrapping this circle a bunch of times. And we do need to include those to get a reasonable answer. So there's just two, in principle, okay, you know, you might say the parameters are B, the size of the throat, and then the fraction that I take of periodic versus antiperiodic. We're just going to view these as fit parameters. We're going to choose them to fit the data as best as we can. And if you do that, this is what you find. So on the left is the wormhole data as a function of tau and tau prime. Fit so that it best approximates the SYK data on the right. I'm taking W equals 0.25, beta equals 20, and the discretization in time is 1000 in this picture. And if you choose B equals 6.4 and F equals 0.32, then this is what you get for the gravity calculations. And visually they look, you know, almost the same. We can of course quantify this. So here's a top-down view. This is the same thing, but with slightly more discretization in time. Here's the SYK data. Here's the wormhole model. This is the residual relative to the SYK answer, the ground truth. And from this color bar, and this grayscale bar down here, you can see the biggest deviation is about 4%. Okay, so just by adjusting these two parameters, we can fit the SYK data with this very simple bulk model to sort of 4% accuracy. And given that beta is not that large, beta equals 20 is not that deep into the conformal regime, I don't know if we should expect to do a lot better than this at this value of beta. We can also calculate the action. So you can convince yourself that the only term which contributes at the classical level is just the length of the geodesic. And it turns out to be something which depends on the weight as weight times log weight. Basically the mass of the heavy particle is proportional to the weight. And so the dashed line is a fit to the data which is in blue dots. And you can see that it captures the Q equals 4 data for beta equals 20 quite well with just these two fitting parameters. So bearing in mind that this is exact, not supposed to be an exact dual of the bulk, the dual of SYK, which is anyways a complicated subject. Apart from predicting the parameter values from first principles, which seems a little hard to do based on what we have right now. But apart from that, we get a nice quantitative match to the SYK data from this sort of two parameter. I say it's a little hard to do because in principle, all these light fields, you have determinants and other contributions that are a little bit hard to calculate. There may be other ingredients in the bulk that we're not including. Modeling the heavy operator as this point particle, maybe there may be some approximation there. So I think it's very interesting to try to push this, but we're already kind of amazed by how well we could capture these calculations with this very simple model. Okay, so let me just go to the end then. Skip all this. You can read about it if you want. So, what did I tell you? First is that I told you about magic, which is an interesting and fun topic. And I told you that we can calculate magic in SYK using path integrals. And I think one nice feature of this is it's one of the very few situations where we can get access to this quantity at large n in an analytically controlled way. So most studies of magic in many-body systems to date have been sort of small n calculations where you put the system on a computer and directly calculate all of these thermal one-point functions or whatever state you have. But here we're actually able to access large n and learn something which is complementary to what these small n studies could tell us. So that's nice. Of course, SYK is sort of solvable, but maybe nearby models in model space still have a lot of magic but are now unsolvable. So it's telling you something about how hard it is to simulate and so on. The second point is that we could model the SYK calculation with this gravity calculation. And this sort of gives you a sort of holographic dual of magic, if you like. Previous work had suggested that magic was related to back reaction and holography. Well, here is sort of seeing that very explicitly. It's this heavy operator which is stabilizing the wormhole, and its action is what's calculating for you this magic measure. And then I didn't talk about this, but I'll just flash it here, that this all actually connects to this story about how do you get closed universes in holography, how do you think about them? And yeah, there's a lot to do, so I hope you'll get involved. Thanks a lot.
I suppose I understand qualitatively. So if I start with the chaotic spin chain, the ground state will not be very magical.
It might be, yeah, I mean, in general, it probably would be.
Usually it won't be if it's gapped. But as you mentioned in your talk about Potts model, if you tune to the conformal point, then it will be very magical. So qualitatively, this SYK story is similar because the low end is you also have conformal mode, which dominates the dynamics, and it's also very magical. So do you want to say that this is a general picture, basically?
Yeah, I think, for pure states with lots of sort of scaling variance in them, I would suspect, that you'd have a lot of magic generic. And for the Potts model, we gave a picture using a tensor network, a Mera tensor network, where we said even if you sort of remove the local magic, you should still have a lot of long-range magic. So I think that's what you really need to kind of guarantee this. So I would expect it to generically be the case, but maybe there's some weird models where it's not true. I'm not sure. Yeah.
Let's see. If we focus on the gravity relation, right?
Yes.
So there was a connection between computing a heavy operator, one-point function.
Yes.
Using wormholes, but
yes.
And gravity, right?
Mm-hmm.
And then when you show this, that heavy operators correlators also appear in the calculation of magic, but I don't see the connection between magic and gravity. Why?
Well, so maybe I can take a step back and say, so what people were thinking about originally, this was Charles Tao and Hama and others and friends, they were thinking about models of the bulk in which you have like a stabilizer code, like the happy code. And that code has a property that its entanglement spectrum is flat. So all running entropies agree with the entanglement entropy. And they said, well, look, in real gravity, that's not true. There's a cosmic brane which back reacts. So we need some non-flatness to model really gravity. And they could quantitatively relate sort of the back reaction or the non-flatness from this brane to the amount of magic you were producing. Okay, so their paper was titled Gravitational Back Reaction is Magic. So here we're sort of seeing that the way you calculate magic is by back reacting this heavy operator on the geometry by stabilizing the wormhole. And so in that sense, I would say it's very synergistic with their story. that it's really the back reaction of gravity, which is encoding the magic somehow. But then very literally, also, it's the action that you calculate, evaluate on the saddle point, which ends up giving you the variance of this operator. So in that sense, it's directly computing the quantity which enters into the robustness of magic.
If not, that's fine.
All right, thanks.